My name is Guanzhong Chen. Here is our Data 2014 Midterm Project Screencast. Handwritten Bengali Grapheme Recognition. Our team name is 42. Our team member has Changcheng Tang, Guanzhong Chen, and Shi Liu. Here is our GitHub repo. And here is our final blog post. Now let's go to our final blog post. The first part is introduction. Bengali is the fifth most spoken language in the world, with hundreds of millions of speakers. This Kaigo competition focuses on the optical recognition of Bengali characters. Let's get familiar with Bengali characters. There are three constituents: grapheme roots, vowel diacritics, and consonant diacritics. Grapheme are graphical units that are sequentially arranged to form words. While English graphemes are comprised of alphabets, Bengali graphemes are more complex with conjuncts and diacritics. As an example with English word proton, the red part here is the vowel diacritics corresponding to O in English. The orange part here is the consonant diacritics corresponding to R in English. Other part are the grapheme roots. Composing them together can form a Bengali character corresponding to our English word proton. To visualize these constituents, let's review our initial blog post. Specifically, we look at the EDA part. There are 168 types of consonant diacritics roots, 11 types of vowel diacritics, and 7 types of consonant diacritics. We can do some visualizations. Among the consonant diacritics root, we chose the top 10 popular roots and plotted them out. Here is the visualization. And for vowel diacritics, we can do the same thing. And here is the visualization. Finally, we do the same thing for consonant diacritics and plotted them out. And here is the visualization. Now let's get back to our final blog post. There are a total of 200,840 data points in the training set. The test set has the same size. In the test time, given a Bengali character, our goal is to classify its three constituents into types. Empirical cases have shown that the convolutional neural network technique is the most popular method working with the image classification task. The next part is method and models. As mentioned above, we will use CNN to tackle this problem. We will focus on the following two parts. First of all, we modify the number of convolutional layers to achieve the best result. Secondly, we apply transfer learning. Transfer learning works with some pre-trained models that already have good accuracies and efficiencies. Then we fine-tune the weights in dense layers of the pre-trained models so it gets adapted to this specific problem. Then our first model will be our baseline model. To understand the baseline model, we refer back to our midway blog post. The purpose of a baseline model is to check if our data structure and initial model are compatible. Therefore, our baseline model will be as simple as a composition of some convolutional layers. It contains 20 convolutional layers with batch normalization and dropouts. This network takes inputs with size 64 by 64 after cropping and resizing. It turns out that after training, our dataset was fitted into the initial model successfully. Here is the result. With 30 epochs of training on a batch of training dataset, the training accuracy and validation accuracy are all above 90%. Specifically, the accuracy of classifying both vowel diacritics and consonant diacritics have reached 97%. Finally, we have built a TensorBoard visualizing the training history. Let's look at the TensorBoard. As figure 1 shows, there are two rows in this TensorBoard. The first row is the classification accuracy of the three constituents. As the graph shows, as the epoch increases, the accuracy increases. The second row is the training loss of the three constituents. As the graph shows, as the epoch increases, the loss decreases. Now let's get back to our final blog post. The next part will be image enhancement. And another member of our group will introduce this to you.
Hi, this is Tangchen Tang. I'm going to talk about some of the enhancements we made on the data and on our model. The first enhancement we tried is tweaking the sharpness of the images. We wished to use this method to make the key pixels more obvious to our neural network. The range we tried is from -3 to +3. As shown in the graph, changing the sharpness of images did change the image quality quite significantly. However, using the enhanced image didn't really bring improvement in the accuracy. Also, the line graphs here suggest high variance in predicting vowel and consonant. This gives us the idea of bagging models in the future. Another approach we tried is resizing. The resize technique we used in the baseline model transformed images from the original rectangle to a square with width of 64. We tried increasing the image size to 96 and 128 to squeeze some extra predictive power. From the comparison, upgrading the size to 96 increased the clarity of images significantly, while the effect of 128 is generally the same as 96. The result after training suggested the same. Size 96 increased root accuracy by 1%, while 128 only scored an increase of 0.5%. Then we tried to improve the structure of our neural network. The first modification was on the convolutional parts. We thought that adding more layers with small number of filters in the beginning of the model can enhance the model's ability to make sense of the images. But after 30 epochs of training, there was no increase in accuracy. The second approach we tried was adding more dense layers after the convolutional layers. The motivation is to enhance our model's ability in translating the information in comp2D into the sense of Bengali characters. To augment this mapping process, we tried different combinations of neuron and dense numbers. Although the accuracy is increasing faster in the first few epochs, the final accuracy stayed generally the same as before. But this experiment gave us another idea of modifying the structure, which is assigning more dense layers for each prediction. The reason we did this is to dedicate more power on predicting each target. After several experiments, we found the optimal combination, adding two more 256 dense layers here, dedicated for root prediction, and putting the additional 256 and 128 dense layers here, dedicated for vowel and consonant prediction. For each layer, we added batch normalization and used leaky ReLU to avoid vanishing gradient, then added dropout to mitigate overfitting. The accuracy is increasing faster in the first few epochs, and after 30 epochs, The models scored a 1.4% increase in root accuracy and a 1% increase in both vowel and consonant accuracy.
Hi, this is Shi. Our fifth approach is transfer learning. Transfer learning is one of the most powerful and widely used methods in deep learning. This is because such pre-trained layers are reusable to solve similar problems like word recognition and image classification. It is likely to have higher training speed and higher accuracy. For this approach of our project, we chose 4 pre-trained models as our convolutional section of our model. Then, the dense layer section is connected after such pre-trained layers. The 4 models are DenseNet 121, VGG19, MobileNet, and ResNet. Here is the training and validation result. The results show that DenseNet performs better over other methods. So our following hyperparameter tuning focuses on DenseNet. Here's the structure demonstration for DenseNet. It has similar structure as our baseline model, but in different filter and dimension sizes. We conducted parameter tuning process for the dense layers after this structure. The result will be discussed later in the result part. The last approach is the bagging. To reduce the variance caused by single model, we implemented bagging strategy by making predictions based on the top 5 models ranked by accuracy. Let's go to Notebook and take a brief look at it. In specific, 5 models gave 5 predictions. And we choose the mode value of the 5 predicted values as our final prediction. Here, we calculated the training accuracy for all data. The bagging accuracy is higher than each of the single models. However, bagging method also requires more computational resources. Here is the result part. The results are based on the training dataset. As we expected, the bagging model's overall accuracy reached 0.9568. This is the proportion of correctness that all 3 constituents are predicted correctly. For single model, the more dense 96 model performs the best. The overall accuracy is 0.950. In addition, we also found that the models with an input size of 128 by 128 did not outperform the models with an input size of 96 by 96. Discussion on future works. We achieved good results for this Bengali Grapheme classification task, and we believe there is still potential possibility that we can improve our model. First, we can have a more scientific parameter tuning process. This requires more time, but hopefully we can obtain better model by selecting a wider range of hyperparameters. Second, we can further improve architecture by applying more transfer learning methods such as EfficientNet. Another aspect is that we can improve the prediction speed by pruning weights or simplifying layers. This is important for industrial and daily life usage of such neural network algorithms, since individuals might not have enough computational resources in their hardware, but they do need to get the word recognition as fast as possible. Alright, that is the end of our screencast. Thanks for watching.